Hey everyone, welcome back to Winston channel. Today we're going to be doing our AP Statistic final review. So this review is basically for those students who's taking AP Statistic exam tomorrow or the week. For your final review, we're going to go through all 9 units of AP Statistic. So, um, uh, this is Winston here, Winston Lin. This slide is made by me, and I'm going to be summarizing and explaining with some examples to you to help you succeed in your AP Statistic exam. Let's go. Let's get into it. So these are the units overview. We're going to go through all 9 units, starting from Unit 1, explain one variable data. So, first of all, introduction to statistic. There's descriptive and inferential statistic. So this descriptive statistic basically is to summarize and describe the feature of a data set. For inferential, it makes prediction or inferences about a population based on a sample. So to begin with, there's two types of data. There's qualitative data, aka known as categorical data, and there's quantitative data. For qualitative data, it's anything that's non-numeric data. For example, our colors or names, which they're not numbers. For quantitative data, any data that are numerical. For example, our heights and our weights. This is as simple as that. Now, graphical representation of data. So basically, Unit 1 will be talking about lots of different kind of different graphs. For example, we have dot plots, histogram, stem and leaf plots, box plots, and bar chart and pie chart, which is the most simple ones. So dot plot is basically display individual data points. You're able to see individual data points. Histogram shows a frequency of distribution. Stem and leaf plots preserve the actual data of the value. Box plots visualize 5 number summary, which are minimum, maximum, Q1, Q3, and median. All right, let's get into it. Dot plot, you can see the entire data are shown on we can see the line here. The data are plotted on the different numbers, and for dot plot we can easily see what's the highest frequency on certain numbers. For example, around 1.5 and 1.45, 1.43, there's most amount of frequency on there. Also, through a dot plot, we can actually try to see the skewness of the graph for this one. When there's don't seem like any skewness because you can see lots of data is in the middle. It's more like a unit model. Now, histogram. So basically, as you can see, this shows the frequency of different data. For example, from age 20 to 30, there's a frequency of total of 2 people, 2 population lives between 20 and 30 age. And for example, from age 50 to 60, there's lies a frequency of 5 people. So there's 5 people within this data set that belongs to the age of 50 and 60. Now, stem and leaf plots. On the left side, you have the stem plot. On the right side, you have the leaf plot. So the stem plot shows the first value of the number. For example, 13, it shows 1. And then 24, it shows a 2 on the stem. Leaf will show the other value. For example, based on the first one, we have the frequency of 13, 14, 16, 17, 18, and 12. And on the fourth one, we can see there's 44, 46. It shows all the data of the events, of the thing you're doing. It shows all the data. Now, box plot. This is really important throughout the AP statistic. You're going to see this all the time. So box plot, these 5 numbers are all really important. We have the minimum and the maximum, which is the range of the data from min to max. And we have now inside we have the interquartile range, the IQR. This is also really important. The entire IQR shows 50% of the data. What does that mean? So basically 50% of the data lies within the IQR range. Now Q1 is 25%, Q3 shows 75%. And we have the median percentile, sorry, and with the median, now the median does not has to be in the middle. It could be here, it could be here. That median will also tell you the skewness. You can also tell the skewness based on the median. All right. Now, summarizing data, we have three important vocabulary to learn. Mean, median, and mode. Mean is the average data of the set. So you add, for example, there's 5 data. You add all 5 data and then divide it by 5. That's your mean. Median is the middle number. It doesn't care about the value of the number. You just list out the 5. For example, there's 5 numbers in the data set. You list out the 5 numbers. And the middle number is the median. You don't add them. You don't do nothing. You do nothing. For the mode is the most frequent value. So it's the value that basically just what it said, frequent. The value that happens the most, appear the most, is the mode, is your mode. Now the measures of spread, the range is the difference between maximum and minimum. So you minus the maximum by the minimum, you get a range. The interquartile range is the middle 50%, which 50% of the data lies within the interquartile range. The variance in standard deviation is to measure the average square deviation and the spread of data from the mean. How spread the data is from the mean. Okay. Now let's take a look at the shape of distribution. So from the left, we have symmetric and skewed. So for symmetric, you can see based on the middle graph, you have the mean, median, and mode all lies in the middle. So it's a perfectly normal graph. There's no skewness, not for the left side. It's skewed to the left. You can see the tail on the left. That's called skew to the left. For skew to the left, this is really important. There's always tests on the AP Statistics exam. I have it before. It always says which is bigger, mean, median, which is bigger, when which is bigger. For example, when it's skewed to the left, the median will be higher than your mean. It will be larger than your mean. Okay. For skew to the right, the median, see, we're greater than the mean. We need to memorize this, okay? This is really important. Now, moving on, uniform. So basically, uniform distribution is basically all the data frequency where lies have similar frequency. You can see there's no skewness. All frequency lies about the same. That's called uniform. Oh wait, sorry, my bad. For skew to the right, the mean should be greater than the median. Okay, the value of mean should be greater than median. I'm sorry. I'm tripping. For skew to the right, the mean should be greater than the median. For skew to the left, the median should be greater than the mean, because you can see for skew to the left, the median is on the right side of the mean. It's higher. It's higher there. Okay, my bad. And by model, very distinguished. 2 peaks. When you see a graph that have 2 peaks, that's a bimodal. All right, moving on. How to identify outliers. So to identify outliers, which we're going to be using IQR. So basically, Q1, that's 25 percentile, minus 1.5 times IQR. Okay, and then Q3 plus 1.5 times IQR. Any values above Q3 plus 1.5 IQR or below Q1 minus 1.5 times IQR is considered as outlier. So how does the outlier impact? It affects the mean, median, range, and standard deviation. So introduction to normal distribution. So the characteristic, it's a bell shape. You can see it's a bell shape. Mean will be equals to median equals to mode. They all lies in the middle with the highest frequency. So the empirical rule states that one standard deviation plus or minus one standard deviation should cover 68% of the data. And then 2 plus or minus standard deviation from the mean should cover 95% of the data. So 95% of the data should lie within 2 standard deviation. For 3 standard deviation, 99.7 data should lies within 3 standard deviation. As simple as that. Now, so using normal distribution, we'll be using z-score and normal tables to find the z-score later on, and then we assessing normality, normal probability plots. So we need to make sure all the data plots are based on are normal probability plots, so they can make the perfect normal distribution shape, the perfect bell shape. So, quick review for Unit 1, key concept and skills. You need to be able to create and interpret graphical display, which include dot plots, histogram, box plots, and etc. You need to be able to identify those and then draw them. You need to be able to calculate and interpret the numerical summaries. You need to be able to calculate mean, calculate median, calculate your range, your IQR, and your standard deviation. You need to be able to understand and address biases in data collection, which will be introduced later, and more introduced in Unit 2, Unit 3. My bad. You need to be able to compare data distribution and identify patterns or outliers. Lastly, you need to be able to apply concepts of normal distribution and z-score for data analysis using the z-table. That's it for Unit 1. Let's go into Unit 2, exploring 2 variable data. Right. Okay. First of all, explanatory versus response variable. So an example for explanatory variable is like in a study of examining the effect of study hours on test scores. The number of study hours would be the explanatory effect, right? For the response variable, it's like let's say in the same study, examination. The same study examining the effect of study hours on test scores. The test score itself would be the response variable. Okay, so that's explanatory versus response variable. Now, categorical versus quantitative relationship. We talked about that before. One is numerical, one is non-numerical data. Okay. Now, for explanatory variable, it is known as the independent variable, which is not dependent from other variables. It is the variable that is believed to influence or cause a change to other variables. The response variable is also known as the dependent variable. It will be affected based on the changes on independent variables. It's a thing that you measure. For example, the examination and test scores. The thing you measure is your response variable. And the thing you measure is the test score. So the test score itself is the response variable. Okay. Now, let's have some examples. For example, experiment on plant growth. The explanatory variable will be the amount of fertilizer applied, which is the independent variable. You can change that variable. It's not the one you measure. For response variable, it's the growth on the plants, which that's what you're trying to measure. That is a response of the experiment. So you can measure on the height or biomass, blah, blah, blah. It depends on the study. And health study. Now, for health study, the explanatory variable will be the amount of daily exercise you apply for them, and the response will be the blood pressure level, because that's what you're trying to find. So that's the response of the experiment. So for marketing analysis, the explanatory will be the advertising budget. Response will be the result you're trying to find, which is the sales revenue. Okay. Now, scatter plots. This is also a really important concept of the unit. It's for the concept of the function of scatter plots is to display the relationship between the two quantitative variables. So, interpreting scatter plots. So now you can see from the slope here. You can see from the slope. The slope basically indicates the amount of changes in the response variable for a 1 unit change in the explanatory variable. It represents the rate of change and shows the direction and the strength of the relationship. So, for example, let's look at this picture right here. For the left one, it's a positive correlation, since we have a slope that's positive. On the middle one is a negative correlation, since it has a it has a negative slope. And then on the right one, it have no correlation because you can see there's no pattern. It's completely random. You don't see any correlation, any patterns, any relationship, no nothing. Now, identifying outliers, you can also identify outliers from scatter plot. For example, one dot that lies far beyond the slope of the relationship is considered as outlier. Now, interpreting the intercept. So the intercept. So basically, for example, intercept. For example, if you have like a equals 50, suggests that if a student does not study at all, for example, if a student does not study at all, that's 0-hour study, right? The predicted test score will be 50, since this is a baseline test score without any studies. Now, for the slope, like for example, if the slope equals b equals 5, let's say the slope is b equals 5, indicates that for each additional hour study, the test score increased by 5 points. This shows a positive relationship between the hours studied and the test score. So every hour you study, you get an increase of 5 points. That's a positive correlate. That's a positive relationship. So moving on, let's look at the correlation. So correlation coefficient, we use R to represent it, is a numerical measure of the direction and strength of a linear relationship. Now the correlation for R ranges from -1 to 1. So basically, the more closer the value is to 1, the more strong the relationship is. For example, let's look at the left side here. When your R equals to 1, it is a perfect positive correlation. So basically, all the dots lies on the slope. It's a perfectly positive correlation. For 0.8, it's 0.8 is close to 1. So it's a highly positive correlation. Still strong. It's still pretty strong, but not perfect, since you can see the dots will lie closely to the actual slope. Now, for 0.3 is a low positive correlation, since you can see all the dots were further away from the slope. But the thing is, you can still see the positive correlation. It's still going up. It's still going to right up. Okay, you can still see the relationship. Now, for no correlation, it's like a last graph on the last slide we saw. You can't see any patterns or relationship. So there's no relationship. So there's no correlation. So your R equals 0. Same thing for negative. The more closer your data is close to -1, the more strong the perfect negative correlation is. The more stronger it is. The more stronger it is. Okay. Linear regression. So like the example I stated before, A and B. A will be the intercept. B will be the slope. A will be the student that does not study at all. B indicates that for each additional study, your test score will be increased by 5. So A will be equals to 50, basically. All right. Now, moving on. Let's look at the equation here. Y is a predicted value of the response variable. X is the explanatory variable. A is the intercept. B is the slope. So this is the example I stated. Imagine a study conducted to determine the effect of our study on test score among high school students. The following linear regression equation is obtained from the data. That's the example I stated before. The responsive variable is the Y, explanatory is the X. 50 will be your explanatory variable, so you start with that, with student with 0 hours of study. Now times plus 5 with 5 points every hour study. So for example, if you're studying for 5 hours, that's 5 times 5. 50 plus 25, 75. You will score a 75 on your test. Just like that. So the residuals. So the residuals is a difference between observed and predicted values. Okay, we use it to assess the fit of regression line and identify patterns or deviations. So for the coefficient for the variable, you'll be using R squared. Is a proportion of the variability in the response variable that is explained by the explanatory variable. So look, we have this residual plot right here. So a residual plot basically shows the difference between the observed response and the fitted response value. The ideal residual plot called the null residual plot. Basically, it shows a random scatter of points forming an approximately constant width band around the identity line. That's the definition. Now, look at this graph. There's no correlation. You can't see any positive and negative blah 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 relationship. There's no correlation. These dots are all scattered, completely random. This is a perfect residual plot. Now, we need to learn two concepts: underestimate and overestimate. For example, underestimate basically means the plot is below the line. Below the line. For overestimate means that the point is above the line, just like that. Okay. The identity line. Yes. So the next concept will be dived into is categorical data analysis. This is a two-way table. Two-way table basically means summarizing data for two categorical variables. Marginal distribution is a distribution of each variable separately. So you can see there's two categorical variables. For example, this one, you have like skateboard, do not like skateboard. That's one, and then we have like snowmobile, do not like snowmobile. So there's two categorical variables compared to at the same time. Next, for unit 2, you'll be learning two new kind of charts. You have the segregated bar chart and the mosaic plots. So these two plots are actually quite similar. The advantage is basically you can see the difference of percentage shown of the two variables at the same time. For example, you can see from the left one, it shows two variables at the same time. How many percent it takes. The blue one shows 35. The pink one, I'm not sure. Male, you can see male. Sorry. So basically, you can see 35% of male likes basketball, and 65% of female prefer likes basketball as well. Favorite sport is basketball. So you can basically see the result of two at the same time. Without start with them. Same thing for the mosaic plot as well. You can see urban and grades. We have like about 60% for both urban and suburban, and rural you can see only about 39%. Based on, in conclusion, you can see the categorical data result at the same time using segregated bar chart and mosaic plots. You're able to draw these plots during the test, which are efficient. They're pretty easy to draw. Just separate them to two percentage. Also, one very important thing is the total need to add up to 100%. That's a key. 70, 30, 60, 40, 35, 35, 65. Total of 100%. Now, association versus causation. So these causation basically implies that one variable directly affects or brings about a change in another variable. Basically, establishing causation also means demonstrating that changes in the explanatory variables cause changes in the response variable. All right, that's for causation. For association, it refers to any relationship between two variables where changes in one variable are related to the changes in another. So they're related. So this relationship can be observed through like statistical measure or like visualization, such as like correlation coefficient and scatter plot, which is the easiest way to do it. Also, causation requires that. So also one important key, very important key, is that causation. Requires that there is an association. Causation requires there is an association between the two variables, but association does not necessarily imply causation. That's really important. Association between two factors can occur both with and without a causal relationship. Okay? Now, the key concepts and skills. You have the ability to create and interpret scatter plots and residual plots, able to calculation and interpretation of correlation and regression coefficients, understanding the condition for the appropriate use of linear regression, the ability to use two-way tables to analyze relationship between categorical variables, and application of a statistical method to describe and quantify relationship between two variables. Also, very importantly, you need to be able to decipher the difference between causation and association and be able to draw the two graphs, the mosaic plot and the scatter plot. Right. Okay, moving on. Now, that's it for Unit 2. Let's move on to Unit 3, shall we? Unit 3, it's called collecting data. This is where the fun thing begins. We're going to be doing samplings. Yes, sir. Now, types of studies. Sorry, let's take a sip of water. Okay, so there's two main types of studies: observational studies and experiments and surveys. So observation studies basically is the gathering data without interfering with the subject. So basically, observe. You observe the subject without putting treatments on it. Don't interfering it. For experiment, obviously, it's impose treatments to observe responses. You give treatments to the subject to observe the response. You're trying to see for a response. You put a treatment on it to see the response. Now, for survey is, well, pretty simple. Just collecting data from a sample of subject through questionnaires, doing survey online, Google form, or interviews. That's survey. You ask for opinion, for response. Okay, this is pretty simple. Now, data collection and sampling. This unit will be covering lots of different types of sampling methods and lots of different types of bias that will occur while doing these kind of sampling. Sampling methods in this unit will cover include simple random sampling, stratified sampling, cluster sampling, and systematic sampling. Bias will be going through understanding different type of bias in sampling. So without further ado, let's get right into it. First, simple random sampling. That's the easiest one. So basically, it's a type of probability sampling in which the researcher randomly selects a subject of participants from the population. It's completely random. Okay. For stratified sampling, basically, the researcher, the experimenter, divide the subject into subgroups called a strata based on the characteristic that they share. For example, the race, the gender. Okay, the strata are based on certain characteristics. Once they are divided into different strata, each subgroup is randomly sampled using another probability sampling method. So each subgroup is randomly sampled. Now, for cluster sampling, is a probability sampling in which you divided a population into clusters, such as like districts or schools, and then randomly select some of these clusters as your sampling. So this is really important. Lots of people mess up the difference between cluster and stratify. For cluster, basically, you need to select the entire clusters of the sample, all population from the cluster. Okay, but for stratified sampling, you select samples from each strata. For example, there's a total of 10 strata, which each strata have 5 people in there. You select 2 dudes from each strata for your experiment. Unlike cluster sampling, where there are 10 clusters, you select the entire one cluster for sampling. That's a key difference. Don't mess one up. This question appears on AP Statistics exam. I almost missed it. Yeah, it took me some time to think about it. But cluster, think of cluster as a cluster. You pick the entire cluster. Okay, for systematic sampling, is a probability sampling method where researchers select members of the population at a regular interval. For example, by selecting every 15th person on the list of a population. See, that's systematic, it's systemized. If the population is in a random order, this can be imitate the benefits, imitate the benefits of simple random sample, basically. If the population is random. Okay. Whew, that's a lot to take in. But not much to memorize. Not much to memorize. Should be fine. All right. Moving on to bias. First, we have the non-response bias. So, non-response bias occurs when an individual select for a participation do not respond or complete the survey. For example, you put out a Google Doc. That dude did not complete it or didn't even respond. They don't give a damn about it. Yes. For example, a survey study, like sending out a mail survey where a significant portion of recipients do not respond, which potentially skewing the results if non-respondents have different opinions than the respondents. So basically that's bias, because maybe the people who actually respond to bias has significantly different opinions than those who did not respond, and then you conclude the result based on those who submit the response. That's bias, because there's a huge amount of people's opinion you did not take account into. Now, for response bias, it's pretty simple. It happens when a participant in a study provide an inaccurate or untruthful response. This is probably the most simple one and the most frequently happen one. Like when you send out surveys, people just randomly pick answers like they don't care. So yeah. Also, a different way to think about it is like, for example, you ask a question. You say like, don't you think our product is excellent? See, like the way you ask or phrase the question may also result in a biased positive response. It's like the experimenter is trying to get a certain response, basically. Okay. Moving on to voluntary response bias. So this arises when the sample consists of individuals who voluntarily choose to participate, which often leading to overrepresentation of strong opinions. What does that mean? Basically, the people who respond are volunteers. So like, this is not accurate because they might have certain bias and they will be representing opinions from other people who did not respond. Because voluntary bias, mostly because for those, just think about like when you respond to something, you volunteer to do something because you like certain things. You like that certain things cause you to do that survey, to pick certain answers, because you're volunteered. You want to do it on your own will. You're not asked for it. So you did it for a reason, basically. Now, for undercoverage bias, this also happens a lot in like all the places. It basically occurs when some members within the population are inadequately represented in the sample. For example, when you're conducting a phone survey that only indicates landline numbers, which exclude those who only have mobile phones. So this automatically eliminate those who only use mobile phones. They didn't even have the chance to respond. They have no idea about the survey. So that's an undercoverage bias, because lots of people did not participate in that survey. That survey only caused some people to be able to respond, to have the ability to respond. Last but not least, we have the selection bias. So for selection bias, this occurs when the sample selected is not representative of the population intended to be analyzed. For example, we're conducting let's say a survey about job satisfaction, but only including the responses from the employees who are currently working, thereby excluding the unemployed or those on leave, because they're not because you did not include all of the subjects. That's selection bias. You select certain people. All right. Now, let's move. That's for bias. Let's move to experimental designs. Some principles for experimental designs. We have control, which is managing outside factors that might influence the outcome. Randomization, using random assignments of treatment to create equivalent groups. Replication, repeating the study or treatment on many units to reduce chance variation. We have blocking, grouping similar experimental units together and randomly assigning treatments within these blocks. So, this is really important of this unit because students, you need to be able to decipher, to identify these three different types of designs. You need to be able to know when is which, when to use which is which is what is what. All right, never mind. So let's start with completely randomized design. This is the easiest one. Basically, subjects are randomly assigned to treatments. Randomly assigned, just random. Now, for randomized block design, subjects are divided into blocks based on a characteristics that subject possessed, and then randomly assigned treatments within each block. Last but not least, match pair design is basically each subject receive both treatment in a random order. That's really important. It's in a random order. You need to mention that other test. Random order or pairs of similar subject receive different treatment. So overall, the concept of random is really, really important. Okay, that's how you decipher the difference. That's the difference of these three designs. Now, let's give an example. A completely randomized design test. An example will be testing the effectiveness of a new drug. So our objective is to determine that if a new drug reduces our blood pressure compared to a placebo. Now the design. Since participants are randomly assigned to either treatment group or a control group, which one will receive the new drug, one will receive the treatment, the other will receive a placebo. Since they are randomly assigned, this is a completely randomized design. The participants are randomly assigned. Randomized block design, for example, testing the effect of fertilizer on crop fields. The objective is to assess the impact of different fertilizer on crop yield while accounting for soil variability. So for the design, since fields are divided into blocks, different blocks, based on the soil type. And now within each block, different kind of fertilizer are randomly assigned to the plots. So the block design is the fields. The fields are divided into different blocks. Now, the last but not least, match pair design. For example, to determine a new teaching method improves student performance compared to the traditional method. So the reason why this is called match pair design is because, for example, each student is paired with another student, who has a similar academic ability. But one student in each pair is randomly assigned to the new teaching method, while the other receives the traditional method. So this is called a match pair design. Yes. Now, this is super important. Random. The importance of randomization. Now, we're in your AP statistics exam, we're conducting a test, not a test, we're trying to make a test. Always says that you need to use a random number generator. That's really important. When you're saying that the participants are randomly assigned to different subjects, to different treatments, always use some context related to random number generator. You use a random number generator to generate 1, 2, 3, 4, 5, 6 for each participant to be assigned with completely random subjects, or so basically everything, the participants need to be random. The subjects, the participants need to be randomly selected. So just always remember to use random number generator to say, just say it in your test. Say it. Yeah, say it. All right. So that was tough. Let's summarize our unit 3. The key concept of skills is to understand the importance of proper study design and different sampling methods, differentiating between observational studies and experiments. But this is pretty easy. Just see which one is observed, which one is experiment. Experiment, you put treatments on there. Observational study, you don't do nothing on it. You look, you observe. Identifying and mitigating various types of bias. You need to be able to identify them, to tell which is what, to be able to define them, to be able to know what caused it. Applying principles of experimental data designed to ensure valid and reliable results. Recognizing the role of randomness in producing unbiased, representative samples. All right. So basically, if you ask me to use one word to describe this unit, the most important concept is randomness. So important. Yeah, we like random. All right. So let's move on to unit 4. Unit 4 is personally, I think it's the hardest unit for me. I struggled a lot. Currently, after AP Statistics, we've been learning calculus, pre-calculus. Also need to do probability, and I still don't understand it. Probability is one of my least favorite. But let's go through it. Let's go. Probability of random variables and probability distribution. So the basic probability. Let's go to some simple vocabs. Let me take a sip of water. So no. Let's start with sample space. So sample space is a sample space collection or set of possible outcomes of a random experiment. Event is an outcome or defined collection of outcomes of a random experiment. So let's look at the picture on the right side here. You have 2 dice. Okay, you have 2 dice. You roll them. The outcome is all of the possible outcomes you can get. There's a total of 36 outcomes. You might get a 1 on this dice. You get a 1 on this dice. You get a 2 on this dice. You get a 3 on this dice. You get a 4 on this dice. You get a, I don't know, 6 on this dice. There's 36 different type of combinations. The sample space, there's 6 outcomes. You have 1, 2, 3, 4, 5, 6. 6. All right. That's pretty easy. That's pretty easy. Now, discrete probability distribution. So the expected variable is the mean of discrete probability distribution. It is the average of the various possible outcomes weighted by their possibilities. That's definition. By definition, yes. So to calculate the expected value, let's look at the example right here. The price for winning a raffle is $1,000. A raffle tickets cost $3, and there are 500 tickets sold. So a ticket has a 0.2% chance of winning. Find the expected value of buying a raffle ticket. So we have 2 events: win and lose, and the value for win is 997, since you minus the costs. The lose is -3, since you spent $3 on a ticket. So the probability of when it is 0.002, probability of losing is 0.998. Now for the expected value equation is the event times the probability of that event that happens. The values that time the probability. So the event that happens is 997 for win, times the probability of win is 0.2%. That gives you a total of 1.994. The value for losing is 99.8%. That value times negative is the probability is times -3, which gives you -2.994. Now, when you add those 2 numbers together, which is negative 1, approximately which is negative 1, that will be your expected value. So when there's more events, just do more work. You just do the same thing, value times the probability, add all of them up, that is your expected value. Okay. Now, one of the most important concepts of this unit is you need to be able to decipher discrete and continuous variable. This is the one I struggle the most. Struggle pretty much when I first studied this unit. So, discrete and continuous variable. They are two types of quantitative variables. Quantitative. Discrete variables represent the counts. For example, the number of objects in a collection. A continuous variable represents measurable amounts. For example, the volume of water or weight. So the main that's a key difference. So let's move on to mutually exclusive and inclusive. Now, if we look at the definition, if we just look at the word here, mutually exclusive basically means that two events, okay, they're exclusive, two events, all right, two events, and not happen at the same time. Okay, we clear? Good. Cannot happen at the same time. That's mutually exclusive. For mutually inclusive is when two events that happen simultaneously, that they are able to happen at the same time. So the equation is for A and B are mutually exclusive is the probability of A intersect B is equal to 0. There's nothing in between A and B. So the opposite probability of A and B is A probability of A plus probability of B. So an example of mutually exclusive is, for example, like rolling a dice. Why? Because, like, for example, you're rolling a dice, okay? You're trying to roll a 2 and roll a 5 on a single dice roll. Is it possible? No, it's not. No, it's not. These two events are therefore mutually exclusive because you cannot roll both a 2 and a 5 at the same time. That's not possible. You can only roll one number at the same time. That means that these two events are mutually exclusive. Another example is like drawing a card from a deck. You're trying to draw a deck of a card, okay? And let's have two events. The events of drawing a heart and an event of drawing a club are mutually exclusive. Because when you draw a card, you get either one of the four suits: club, spades, flower, diamond, hearts. Yeah, you only get one suit. When you draw a card, you get one suit. You cannot draw two suits at the same time. That don't work together. It don't work that way. So that means these two events, drawing a heart and a club, these two events are mutually exclusive. For mutually inclusive, an example would be trying to draw a card from a deck. The events, same thing, trying to draw a card from a deck. The events of drawing a red card and the event of drawing a king are mutually inclusive. Reason why is because you're able to draw a king of hearts. You're able to draw a card that's king, also it's hearts. So these two events can happen at the same time. When they can happen at the same time, it is mutually inclusive. Just like that. Pretty simple. Now, for conditional probability, basically it's the probability of A occurring given that B has already occurred. So it shows as P probability A denote slash B. So the back number B is the one that's given. You're given B to find a probability A. The equation is down here. Oh, by the way, all the equations are given on your formula sheet, so that's pretty good. So the equation is the probability of A intersect B, the probability of A, B happens at the same time, over the probability of B. That's how you find the answer. So Key concept, independence, really important. Two events A and B are independent if probability of A given B equals to probability A times probability of B given A. This means that the occurrence of one event does not affect the probability of the others, not dependence. If probability of A given B does not equal probability of A, right, then the events are dependent. They're considered dependent, meaning the occurrence of one event affects the probability of the others. It's really different. You may be able to know whether they are independent or dependent. Okay, let's move on to binomial probability distribution. So binomial experiment is an experiment using a fixed number of independent trials with only two outcomes. This is really important because these experiments have outcomes that are defined as either success or failed. That's an example. Okay, it can only ever be success and only ever be failure. For example, a coin flip. It can only be head or tail. You can only have two possible outcomes. So, this is the equation right here. N is the number of trials, X is the number of success, P the probability of getting a success in one trial, Q is the probability of getting a failure in one trial. Let's move on. So let's look at a question, an example question. A quality control engineer at a factory finds that 5% of the products produced are defective. If she randomly selects 10 products from the population line, what is the probability that exactly 2 of them are defective? So, as to see in the question, let's just list out the variables here. N is 10, is the number of products selected. K is 2, the number of defective product we're interested in. P is the probability of the product that's defective, which is 0.05%. That's 5%, 0.05. 0.05. Y minus P. So Y minus 0.05 is gives you it gives you 95%. That's the probability that product is not defective. After you have all the values, just blah blah blah, plug them into the equation, and you'll find the answer. The probability that exactly 2 out of 10 selected are defective is approximately 7.45%. Just plug in the number and use your calculator, TI-84, or CAS, whatever you're using, and you'll find the answer easily. Okay. Now, the most important concept, in my opinion, of this unit is the probability distribution. You have PDF and CDF. So, PDF stands for probability density function, and it is used to describe the likelihood of a continuous random variable taking on a particular value. Remember, it's particular value, exactly a value is looking for. So, for CDF, it stands for cumulative distribution function. You can tell from cumulative. It's a function that a random variable x denoted as f of x gives the probability that x will take on a value less than or equal to a given input of x. So in the question, you will see something like at the most, least. That's the kind of CDF you're looking for. All right. Let's move on. Now, normal versus binomial. The main difference, this is also important because on your AP's test, you need to be able to tell that when to use normal CDF, normal PDF, binomial CDF. You need to be able to know when to use normal, when to use binomial. Okay. So, the main difference between a binomial distribution and a normal distribution is that binomial is discrete, whereas the normal distribution is continuous. So basically it means that the binomial distribution has a finite amount of events, where the normal distribution has an infinite amount infinite number of events. Okay, And that sounds very vivid. Let's just go straight into some example questions so you'll understand it. All right. If you have no idea what I'm talking about, let's just go straight into the question here. So this question is about normal CDF PDF here. In a population of adults, the height of the individual following a narrow mode distribution with a mean of 68 inches and a standard deviation of 3 inches, what is the probability that a randomly selected adult is shorter than 72 inches? Now, this is a normal CDF questions because why is the CDF? People, what is the CDF? Yes, you know why, right? Because it says shorter than 72 inches. We're looking at a cumulative data. It's not asking a specific data. So all you need to do is just pull your TI-84 or whatever calculator you're using. Go to second, press the vars, which is this for distribution. Press enter normal CDF. For your lower bound, use negative. It can be anything, but I recommend use just -1 to the power of 99, or use like negative. Or you just use like -10,000, -1 million. Your upper bound will be 72 inches because that's the max here. You want to see 72 is the max. You want to see anything be shorter before 72. So your 72 will be the max. And and then for your mu will be 68 inches. Standard deviation will be using 3 since those are given. Now just plug those into your calculator. You will find the answer. So sometimes on the test, you can just leave your answer like this. Just type a normal CDF and then alongside with a variable. This, you don't, sometimes you need the answer, sometimes. So for PDF, let's look at the question. What is the probability density function value at when x is equal to 70 inches for the same population of adults described above? You see the difference? This says x equals 70 inches. We're looking exactly 70. We want to find the population x equal to 70 inches. That's one value. We're trying to find that one, exactly that value. That's when you know you want to use PDF. Looking at that value. So PDF, just go same thing. Second vars. You press normal PDF. You press in the x value, which is 70, and your mean, which is given, is 68. And then your standard deviation, 3. Type it in, enter. Actually, I'll do it right now. 70. I'm do it right now. So 70, 68, 3. Just plug in the equation. See? Now you can see it just like that. See it? So the probability is 0.106. Okay? Just like that. Very simple. So, for binomial CDF here, difference here. Now let's recall again. What's the difference between binomial and normal? Binomial has a finite amount of events, where normal has an infinite numbers of events. So for this one here, let's look at the question here. In a binomial event with n equals 10 trials and success probability of 0.7, what is the probability of having at most 5 successes? Do you see the key word? At most. That's the key. That's when you want to use binomial and use CDF. It says at most. It's not a value. Okay? At the most 5 successes. So, same thing. You enter the parameters. Binomial CDF, which can be found by pressing second and vars. Find binomial CDF. Enter the value of trials, which is 10. The p-value, the probability, which is 0.7, and your x value, which is 5. You want at most 5 successes. Now, the probability of exactly 3 successes in the same binomial experiments described in the previous question. For this one, you see the keyword right here? Exactly 3 successes. We're trying to find one number, one single digit, one single subject. Exactly 3. You see the keyword, exactly 3. So In that case, you use binom PDF. Go to second var, binom PDF. Same things, enter your trials, P and X value, and you will find the answer. All right. Last but not least, we have the geometric distribution. So basically, to be simple, the geometric distribution is basically a probability distribution that basically describes the number of trials needed to achieve the first successes. Okay, the first success in a sequence of independent trials, where each trial has also only have two possible outcomes, like success and failures, and the probability of success remain constant across all the trials. Are we clear? So that's the simple definition. Now we can hear each trial has the same probability of successes. That's also really important. You cannot change the probability. No. Okay, let's look at an example. Suppose you're flipping a fair coin repeatedly until you get a head. What is the probability that you will get exactly 3 flips to get the first head? As you can see, the keyword here, to get the first heads. That's the keyword. To get the first one. So that's when you know. You want to use geometric sequence, geometric here. So basically, enter the x value, the number of trials, and value of p, which is for genome x and p. Now you see it says exactly 3 flips. Sorry, I didn't include it on here. I didn't include the genome things. So we're gonna use the genome PDF. Now you know why, right? You know why you use genome PDF? Exactly 3 flips. Exactly 3. Exactly 3. So you go to second var, go to genome PDF. Number of trials is 3. The x value, flip a coin, is 0.5%. 0.5. That should gives you 12.5%. Just like that. Okay? So, key concept. You need to be able to master the probability concept and their application in solving problems. Understanding the probabilities and characteristics of discrete and continuous probability distribution. Application of probability distribution in real-world scenarios, which is you'll be seeing those on the test, including binomial experiment, sampling distribution, and central limit theorem. We'll cover that later in the unit. I include that on here because that's important. That's kind of goes across different units. So yeah, I think I should include down here, but we'll talk about that later. Able to interpretation of expected values, variance, and standard deviation in the context of probability distribution. Last but not least, need to have the ability to use statistical software calculators to perform calculations involving probability distribution. Because, hey guys, you have no way to calculate those probabilities without knowing how to use your TI-84. And you're able to use your tool wisely. Okay. TI-84 is like your weapon. Yeah, weapon. All right, very important. So, that's it for Unit 5. Unit 4. You guys survived? I hope so. All right, let's move on to Unit 5. We're going to be talking about sampling distribution, which is where the fun part begins. So the sampling distribution is a distribution of a sample statistic. For example, a mean, a proportion, calculated from all possible samples of a certain size from a population. Okay, so for central limit theorem, okay, central limit theorem, the samples are randomly selected from a population. We know that. That's central limit theorem. The sample size are sufficiently large. Typically, it needs to be large. So, for example, the number of population need to be above 30 for a reasonably symmetric population distribution. Okay, so that's for central limit theorem. If that's true, if your population is above 30, then you can assume that the population distribution is approximately normal. Okay, we're clear? So, uh, so the central limit theorem basically is a fundamental concept in statistics that describe the behavior of the sampling distribution of the sample mean when drawing repeated random samples from a population. Basically, it states that regardless of the shape of the distribution, the sampling distribution of the sample mean approaches a normal distribution. As the sample size increases, we good on that? As the sample size increases. Okay, so a central limit theorem basically states that as the sample size increases, the sampling distribution of the sample mean become uh wait sorry okay never mind. So basically it states that when sample size increases, the sample distribution of the sample mean becomes increasingly normal in terms of shape, regardless of the shape of the population distribution. Okay, so let's move on to sampling distribution. This is the equation that will be used, and these are given on your formula sheet on your AP statistic exam. There's no need to memorize these. So, sampling distribution for sample proportion. Let's look at example right away. A manufacturer claims that 70% of its product meet quality standard. To investigate this claim, a quality control manager randomly selects 200 products from the production line and finds that 140 of them meets the standard. A. What is the sample proportion of the product that meets quality standard in this sample? B. Based on the sample proportion, calculate the standard error in the sample proportion. So let's look at the. So these are the. So let's look at how you solve it here. First, sample proportion. Now proportion, important, very important. When you see proportion, you use p hat. That's different from population. Proportion, you use p hat. So sample proportion based on the equation is the number of successes divided by sample size, which 140 divided by 200 will give you 0.7. Now, for the equation, we see from the formula sheet, the standard error will be p hat, the square root of p hat over 1 minus p hat over n. So basically, we have 0.7 times 1 minus 0.7 over 200. So that's 0.7 times 30 over 200. And then you square root that number, which the standard error will be approximately 0.0324. Just plug it in the equation. Now, check conditions. This is also really important. Whenever you're performing different tests, always be sure to check conditions. Except if the question itself stated that assume all the conditions are meet, then you don't need to waste your time checking conditions. But for most of the time, remember to check conditions before you start going through your tests. Okay. So we have success and failure. That's the first that you see is the expected number of the success and failure need to be both greater than 10. So n times p need to be greater than 10. The number times the probability need to be above than 10 for both. Now the 10% rule, 10% condition is that each sample need to be less than 10% of the total population. For example, you pick 10 Oreos for your test. 10 Oreos is 100% less than 10% of total Oreos exist in this world. Okay, that's 10% rule. Randomization. This is the most important one. The samples obtained is through the random sample technique. So like the samples are obtained. The method obtained is completely random. Needs to be obtained completely random. Now, sampling distribution of the sample mean. And if the population is normally distributed or the sample size is large, thanks to our central limit theorem, greater than 30, the sample distribution of the sample mean will be approximately normal. If the population standard deviation is known, the standard error of the mean, which is standard deviation over the square root of n, and if the population standard deviation is unknown, the sample standard deviation as is used, and the standard error is s standard deviation over the square root of n. And sample distribution of the sample proportion. When dealing with categorical data, the sample proportion, which is the p hat, is a statistic of interest. So the sampling distribution of the sample proportion is approximate at a normal distribution when certain conditions are met, like we mentioned before, the conditions. The standard error of the proportion, SE, is equal to square root of p times q over n, which we saw that from based on the you can see that from the formula sheet, where p is a population proportion and q is 1 minus p. So if q is 40, if p is 40, q will be 1 minus 40, which is 60. Now, hypothesis testing. In hypothesis testing, we use information from a sampling distribution to make decisions on whether to reject or fail to reject the null hypothesis about a population parameter. So let's review. The key concept is skills. So now, understanding sampling distributions, okay? So basically, you need to learn about the concept of sampling distributions, which represent the distribution of a sample statistic, like a mean or population, over repeated samples taken from the same population. Central limit theorem, like I mentioned before, is a fundamental concept that states that regardless of the shape of the population, the sampling distribution of the sample mean approaches a normal distribution as the sample size increases. Calculating sampling distributions, you'll be able to interpret sampling distribution for both sample means and proportion. You'll be able to learn the standard error as a measure of the variability of sample statistic. That's what a standard error is. Application of sampling distribution. You need to be able to apply these kind of understanding of sample distribution to make inferences about population parameter. You'll be able to learn how to calculate the probabilities and the confidence interval, which I'll mention confidence interval will be mentioned in the next unit. Extremely important, using sampling distribution. Last but not least, critical thinking and problem-solving skills. Throughout this unit, you'll be able to develop critical thinking skills by applying statistic concepts to real-world scenarios, because that's the whole point of statistics, is to apply these knowledge to real-world scenarios, to combat, to face real-world issues, real-world problems. Since all the problems on your AP statistics exam are random example from real life, they're realistic most of the time. The questions are realistic and from real life. So that's really important. You'll be able to think critically, and your problem-solving skills need to be really good. Okay. So that's tough. That's it for Unit 5. Now let me take a sip of water before we move on to Unit 6. Okay, so Unit 6. We'll be talking about inference for categorical data, proportion. All right. So, see what I told you. Confidence interval. Confidence interval. Super important. A confidence interval is a range of values derived from sample data that is likely to contain the true proportion parameter within a certain level of confidence. In the context of proportion, a confidence interval provides an estimate of the range within the true population where the proportion lies. So let's look at an example right away and you understand what I'm talking about. A survey was conducted to estimate the proportion of adults in the city who support a new public transportation initiative. Out of a random sample of 500 adults, 320 of them expressed support for the initiative. Now the question is, calculate a 95% confidence interval for the true proportion of adults in the city who support the initiative. It's actually pretty simple. So let's go through it one by one. The standard proportion P, 320 over 500, which is 64%. The sample size of 500, confidence level, we're using a 0.95, 95% confidence interval. So to calculate a confidence interval, you'll be using your z-score, z, times standard error. Okay? So how does that work? The standard error, given the same equation from before, you can see square root of p over q, p times q over n. So move on. So all you need to do is plug in the value of p and q, which in this case is 0.64 and 0.36. Divide that by 500, square root of that, that gives you 0.0206. Now, for 95% confidence interval, if you look at your z table, or you can even use your calculator to find it. That is approximately 1.96. That's your z-score times 0.0206, which is the standard error. That gives you a value of 0.0404. Now your confidence interval will be 0.64 plus or minus 0.0406. Just as simple as that. So the conclusion. Now this is the same structure here. Just memorize this structure and use this kind of structure for a conclusion for all kind of confidence interval questions. So your conclusion looks to say like this: we are 95% confident that the true proportion of adults in the city who support initiative is approximately. Remember to say approximately. Super important. 0.5996 to 0.6804. Just like that. Super easy, right? Moving on, p-value. Let's talk about p-value. So, the p-value is the probability of obtaining a test statistic as extreme as, or more extreme than one observed in the sample data, assuming that the null hypothesis is true. So, less than a significant level, so p-value. When the p-value is less than a significant level, you reject the null hypothesis. When it is greater than a significant level, you accept the null hypothesis. Moving on. So, tests for population proportion. Now, this is a step. So, first, null hypothesis. State your null hypothesis. This is your default assumption, basically. It usually states that there's no effect or no difference for a proportion. It often states that the population proportion is equal to a specific value. For example, your null hypothesis is like your population proportion is 0.5. Just an example. Next, you say your alternative hypothesis, which you could say H1 or HA. That is what you want to find evidence for. It could be a claim that there is an effect or a difference. No hypothesis, there's no difference. Your alternative hypothesis is there's a difference. For example, this case will be your P is not equals to 0.5. The population proportion is not equal to 0.5. Now, next time you'll be choosing significant levels. Now, usually, all the time, if the question does not give you the significant level for the test, use 0.05. Oh, that's your default number. That's your matching number. Use 0.05. Unless the question asks you to use which kind of significance level, or else always use 0.05. Now, next step will be checking conditions. For conducting a test for population proportion, basically it includes random sampling. So it ensures that the sample is obtained through random sampling method. We mentioned that before. Also, independence. Individuals' observation in the sample should be independent of each other. For proportion, Basically, this means that the sample size should be less than 10% of the population size. I mentioned that before with the Oreo example. Now, large enough. The sample size needs to be large enough. To use the normal approximation hypothesis testing, the sample size should be sufficiently large. A common guideline is that the n times p, like I mentioned before, your n times p need to be greater than 10. N times q also be greater than 10. That's the ideal situation. Next up, we collect data and calculate your test statistic. So this is where the calculation begins. So collect a random sample from a population and calculate the sample proportion, which is your p hat. Now, calculate the test statistic. Usually, for a z-score, you'll be using z-score because whole point is to try to find a z-score or a t-score, which we'll mention later on in the unit. Usually, if a z-score is for a larger sample, t-score is for a smaller sample size. We'll evaluate this more in unit 7. Yes, sir. Okay. Let's just head to an example. So, suppose we want to test whether the proportion of students who prefer online learning is different from 0.5. Collect a random sample of 200 students and find that 120 of them prefer online learning. So, hypothesis. Your null hypothesis and your alternative hypothesis. Your P equals to 0.5. HA, our alternative hypothesis, is when P does not equals to 0.5, because that's what you're trying to find. So your sample proportion, P hat, is equals 120 divided by 200. That's 0.6, 60%. Next up, we'll be checking conditions. So, we'll be checking conditions. So first up, we'll be using random sampling. Of course, we need to make sure that the samples chosen are random. Next, we'll be seeing if the sample size are large enough. So it'll be NP 200 times 0.5 equals 100. For Q, 1 minus Q, that's 50, also 50. So 200 times 0.5 is also equals 100. Since both of these values are greater than 10, this is good. The sample size is large enough. Next, we'll be going through calculations here. So we have obtained all the data we need here. We'll be using z-score to find it. So z-score to find. So the z-score equation also can be found on your formula sheet. P hat minus P over the square root of P times Q over N. So we'll plug in all the data plug in all the data to find the z, which gives us a value of 2.83. That's your z value. After finding the z value, the next step is to find the p value, because that's the value that you are trying to compare with your significant level. If the p value is less than significant level, you reject null hypothesis. If it's greater than significant level, you accept the null hypothesis. All right. So, how do you find the p-value from your z-score? Actually, pretty simple. You use normal CDF to find the p-value. In this case, you do 1 minus normal CDF to actually find the p-value. Okay. So basically, what you should do is enter, pull your calculator, go to second distribution, go to normal CDF, enter the lower bound and the upper bound. Since this test is a two-tailed test, you will need to enter the negative of the test statistic as the lower bound and the positive statistic as the upper bound. For example, if the test statistic we found z-score is 2.83, enter negative 2.83 as your lower bound, and the upper bound will be 2.83. Now your mean and standard deviation 0 and 1, since they're not given. After blah blah blah, press in all those numbers, paste, that gives you a value of 0.004. That's your p-value. Now, since you have the p-value, compare that p-value with 1.96, which is our significant level, 0.05. Since 0.004 is less than 1.96, we reject the null hypothesis. Therefore, so our conclusion should look something like this. Based on sample data, there is sufficient evidence to conclude that the proportion of students who prefer online learning is different from 0.5. Now, one key thing to remember, you need to say sufficient evidence. The word evidence is super important. Okay, always make sure you say something like sufficient evidence along those lines. Now, difference. So, the main difference between proportion and sample proportion is that a population proportion represents the proportion of individuals in a population with a certain characteristics. On the other hand, sample proportion p hat is used to estimate the proportion is used to estimate the population proportion, and is calculated as the number of individuals in the samples with the characteristics of the same interest, and divided by the sample size. Divided by the sample size is super important. Next, test for a difference in population. So I'm just going to briefly go through the steps again. First, the hypothesis. This is for test for difference in population. For no hypothesis, basically, it typically states that there is no difference in the proportion of the two population. And while the alternative hypothesis, which is HA, suggests that there is a difference, and it can be one-tailed or two-tailed. For the previous example, it's a two-tailed. Now, test statistic. The test statistic for a difference in population proportion follows a standard normal distribution. When the sample sizes are sufficiently large, it is calculated using formula for the difference in sample proportion and the standard error. Next step, condition for inference. Same thing, random sampling, independence, sample size. I'm not going to mention that again. Check conditions. Always check those three conditions here. Unless the question mentioned, the condition assume the conditions are checked. Now, p-value conclusion. The p-value is calculated from the test statistic, which is using the z-score, and is used or the t-score later, and is used to determine the strength of the evidence against the null hypothesis. If the p-hypothesis is less than the chosen significant value, we reject it. If it's larger than the alpha, which is if it's larger than the significant value, we will favor the null hypothesis. We do not reject the null hypothesis. Next, let's talk about confidence interval. So, confidence interval for a difference in population proportion can be constructed to estimate the range of plausible values for the true differences. So, last but not least, interpretation. You interpret the result. The results are interpreted in the context of the problem to draw conclusions about the difference in proportion between the two populations. That's briefly state how you're supposed to test for the difference in population. Key points and skills. Finally, understand the process of conducting hypothesis tests and constructing the confidence interval for population proportion. You still need to be able to be familiar with the conditions required for valid inference and how to check for their satisfaction. Be sure to check all those conditions. Super important. Practice interpreting the results of hypothesis tests and confidence interval in the context of specific problems being studied. You'll be able to master the calculation of test statistic, the p-value, and confidence interval for proportion using appropriate formulas or technology. TI-84, your weapon. Moving on, Unit 7, Conference for Quantitative Data. This time we'll be talking about mean. So the t-test. Now t-test, not z-test. T-test here. And t-set is basically a statistical test that compares the mean of two samples. It is used in hypothesis testing with a null hypothesis. With a null hypothesis that the difference in a group means is 0, and an alternate hypothesis that the difference in group mean is different from 0. Now, t-test. There's two types of t-tests. Independent sample t-test, used when you want to compare the mean of two independent groups to see if they're significantly different from each other. With paired sample t-test, used when you want to compare the means of two related groups to see if they are significantly different from each other. And this group is often used when the same group is measured at two different points in time or under two different conditions. Now, super important, TVSV. For a z-test, it is used if the population variance is known, or if the sample size is larger than 30 for an unknown population variance. If the sample size is less than 30 and the population variance is unknown, we must use the t-test. So simply to say it is that the t-test is employed to compare means of small samples. T is for small samples, usually when the sample size is less than 30, while the t-test is used to compare means of larger samples, typically when it's greater than 30. That's an easy way to decipher when to use t and z-test. For t-test, the parameter, a number that describes some characteristics of the population sampling variability. The value of statistic varies in repeated random sampling. We need to estimate sampling variability so we know how to close our estimates to the truth. You see margin of error. An unbiased estimator means that a sampling distribution of a statistic is equal to the true value of the parameter. For a biased estimator, a statistic is consistently higher or lower than the parameter. Moving on, the most important concept of this unit is type 1 error versus type 2 error. To be simple, type 1 error is to reject a null hypothesis that's actually true. Type 2 error is to fail to reject a null hypothesis that's actually false. Let's start with type 1 error, also known as a false positive. A type 1 error occurs when you reject a null hypothesis that is actually true. In other words, it's when you conclude that there is a significant effect or difference when there isn't one in reality. The probability of committing a type 1 error is denoted by the alpha, which is typically set at 0.05. Now, for example, in a medical test for disease, a type 1 error will be concluding that a person has the disease when they actually do not. That's a false alarm. That's a false claim. On the other hand, type 2 is also known as a false negative. This we conclude when there is no significant effect or difference when there actually is one in reality. Now, an example of the same example will be in a medical test for a disease. A type 2 error will be failing to diagnose a person with the disease when they actually have it, which missing the disease, right? You fail to detect it, fail to diagnose that the patient has a disease when they actually have it. That's type 2 error. You fail to reject the null hypothesis when it's actually false. So, let's look at the question here. Difference in population mean here. Now, we're giving a bunch of data here. But the most important thing here, okay, let's just read through the questions here. Research conducted study investigated whether local car dealers tend to charge women more than men for the same car model. Using information from counter-text collector requires researcher randomly selects one man and one woman from among everyone who had purchased the same model of an identically equipped car from the same dealer. The process was repeated for a total of 8 randomly selected car models. So, basically, all the graph is actually quite redundant. The main point you want to find here is the difference, because this question is asking the differences mean. So the question is asking, do the data provide convincing evidence that non-diagonal women pay more than men for paying car models? Sorry, my face thing blocked the rest of the question, but it's along those lines here. So first step. Let your mu difference. your mean difference represents the population mean difference in purchase price, which is in this case woman minus men. For identically equivalent cars for the same model, sold to both men and women by the same dealer in the same country. Step 2, the hypotheses to be tested are your H will be 0, mu difference is equals 0 versus your alternate hypothesis, where your mu difference is greater than 0. So the difference is 0. There's no difference between men and women. Woman minus men, no difference. That's when it equals to 0. When the mu difference is greater than 0 means there's a difference. Okay? So in this case, the appropriate procedure is the paired t-test. The condition for the paired t-test are condition check. Remember, the sample is randomly selected from the population. They are randomly selected. Secondly, the population of difference is normally distributed since the sample size is large enough. Now, to find the t-test statistic, the t-test is also given on the equation. You just plug in all the values and you find your t, which in this case is 3.12 here. Now, for the p-value. Now, how do you find p-value when you're given t-value? So, instead of using normal distribution, normal CDF, that's for z-score, you use t-CDF. So, go to TCDF, plug in the value. Lower bound will be negative 1 to the power of 99. Your upper bound will be 3.12. That's your t-score. And your degrees of freedom, 8 minus 1, based on the question, which is 7. You plug all those values in with 1 minus TCDF, you get a value of 0.008. Now, same thing. Since this value is so small, right? It's so small. It's so smaller than 0.05, so close to 0. We reject the null hypothesis, obviously. The data how do you conclude it? You say that the data provide convincing evidence that on average women pay more than men in the country for the same car model. See the key word, convincing evidence. Make sure you say that. Just like that. It's not that complicated. So, for the key concept and skills of Unit 7, we'll learn hypothesis testing for means here. And you learn how to set up and conduct hypothesis tests for population mean. You understand the null hypothesis and the alternative hypothesis. Now, next, confidence interval. You will be able to calculate and interpret confidence interval. For population mean. You may recognize the relationship between confidence levels, sample size, and margin of error. T-distribution. You be able to understand the use of t-distribution for inference when the population standard deviation is unknown, when you don't know what the standard deviation is, and or the sample size is small. That's when you know you want to use t-distribution. The t-test. Identify degrees of freedom and their impact on the shape of the t-distribution. Next, we'll be looking at the condition for inference. You'll be checking and verify conditions for valid inference, which is the randomness of the sample, normality of the population distribution, and the independence of the observation. Also, you apply the central limit theorem for larger sample size, which the population need to be greater than 30. Last but not least, comparing two means. You'll be able to conduct inference for the difference between the two population means using independent samples, which is the question we just did. So that's it for the brief summarization for Unit 7. 2 more units to go. You guys still alive? Let's do it. 2 more units to go. Unit 8. Inference for categorical data. Chi-square test. Now, chi-square test is actually one of the easiest units, I think, personally. The purpose of chi-square test is to use it to determine if there is a significant association between categorical variables, or if a categorical variables follows a specified distribution. Now, this entire unit, all you know, the main concept is you know the 3 different type of chi-square tests, and you need to be able to decipher, to identify, to tell when to use which one. See, this is the hardest thing for AP statistics. Like, you know the concept, you memorize the concept, but the hardest thing for AP stats is you need to know when to use which test, when to use which concept. That's the hardest thing in AP stats. So, chi-square good to fit test here is to test if a single categorical variable follows a specific distribution. For chi-square test of independence, tests if 2 categorical variables are independent. For chi-square test for homogeneity is to test if the distribution of a categorical variables is the same across different population. So let's move on. Let's start with goodness to fit test. So we want to determine if the distribution of a single categorical variables matches a specific theoretical distribution. That's when you use good to fit. An example include testing if a die is fair, or if the distribution of colors in the back of M&Ms matches the company's claim, or if a categorical sample response followed a predicted distribution. Another example would be like if you have a bag of like Skittles and you want to test if the proportion of each color matches the company's stated proportion. You want to match, see if the color of the Skittles you get from the bag matches what the company claims. How many company stated how many colors of Skittles should be are available in each pack. You're trying to compare with the company's stated proportion. So for good to fit test, the null hypothesis HO will be observed frequency fit the specified distribution. The alternate hypothesis is observed frequency that do not fit this specified distribution. Moving on, conditions, randomness, as well. Expected counts, again, the expected should be greater than at least 5. Now, this is the equation. Looks dirty, looks disgusting, I know, this stupid equation. But hey, you don't need to memorize it. It's on your formula sheet. What's even better is actually you don't need to use these kind of formulas. All you can do is just write them down. You don't need to actually list them out because you can actually find all the things from a TI, from chi-square. You can find all the answers by plugging values in your calculator. Moving on, chi-square test for independence. So this is used when you want to determine if there is an association between 2 categorical variables. An example include like what's one example? So like an example. Okay, we'll move an example later. I'm gonna say the null hypothesis first. The null hypothesis will be 2 variables are independent. Alternative is the 2 variables are not independent. So, sorry. So let's look at the example real quick here. So an example for test of independence will be something like examining if gender is related to voting preference. Okay. Or if smoking status is related to incidence of lung disease, or if a type of exercise is related to weight loss category. That's there's 2 categorical data, 2 category. That's chi-square test for independence. So also this is really important. Contingency table. Sorry, I pronounce. Is used to organize observed frequency for 2 categorical variables. So let's look at the example. We have boy or girl, and like sneaker does not like sneakers. To find the expected counts, you times the row total times the column total divided by the gram total. So in this case, if you want to find the boys and like sneakers, you type 73 times 51 divided by 100. For girls, you took 27 times 49 divided by 100. That's how you find the expected counts for a chi-square test. So the degrees of freedom, oh sorry for the D, is rho minus 1 times column minus 1. So R is the number of rows, C is the number of columns. So on the previous example, there's two variable, boys and girls, two variable, like sneaker, do not like sneakers. So 2 minus 1, 1, and 2 minus 1 for column is also 1. 1 minus 1 is 1. So the degree of freedom is 1. Condition, also randomness and expected counts. Each expected count should be at least 5. We mentioned conditions like 100 times already. Make sure you do the condition test. Okay, last but not least, chi-square test for homogeneity. Homogeneity. When you use it, you want to use it when you want to determine if the distribution of the categorical variable is the same across several populations. For example, an example will be like comparing the distribution of blood types across different ethnic groups, voter preferences across different regions, or customer satisfaction rating across different stores or even different countries, different populations. That's for homogeneity. The null hypothesis is basically the same. The distribution are the same across different populations. Alternative will be the distribution are not the same across different population. So test of homogeneity is quite similar to independence test. The test statistic and condition are the same as those of the chi-square test for independence. Difference is used to compare the distribution of single categorical variables across different population. Now, interpreting chi-square tests. Now, the p-value is the probability of obtaining a chi-square statistic as extreme as or more extreme than the observed value if the null hypothesis is true. So how do you decide? Same thing here. If the p-value is less than the significant level, you'll reject the null hypothesis. If the p-value is greater than or equal to the significant level, do not reject the null hypothesis. You will accept the null hypothesis. So, a summary. This is the graph I made. Summary here. We have the three tests: good to fit, independence, homogeneity. The purpose of good to fit is to test if a single categorical variable matches a specified distribution. Variable is a one categorical variable. Example, testing if a dice is fair. Test for independence to test if there's an association between two categorical variables. And it's the two categorical variables. Example will be testing if a gender is related to a product preference. Last but not least, test for homogeneity to test if the distribution of its categorical variables is the same across multiple population. There's a one categorical variables across multiple population. That's the variables. Example will be comparing the satisfaction of voters across different stores. Voters of different of customers across different stores or different regions. Stores from different regions. Now, some common mistakes and tips of this unit here. First of all, small expected counts here. You need to ensure that all expected counts are at least 5 to satisfy the condition. Independence assumption. You need to ensure that the samples are independent, especially in the test for independence. Last but not least, the context matter. That's the key. That's what I said in the beginning here. You'll be always able to interpret the result of the chi-square test in the context of the data and the research question. Also, you're able to decipher when to use what chi-square, when to use good to fit, when to use homogeneity, when to use what's the last? When to use independence. Right. All right. Now, our key concept of concept skills. We have learned the three types of chi-square tests: homogeneity, test for independence, and goodness to fit. And we have conditions and assumptions here. Concept here. We need to ensure the validity of chi-square tests by checking that the expected counts are at least 5 and the data is from a random sample. The skill you need, of course, you need to verify assumptions and correctly interpret results based on the conditions. Interpreting results. Understand the significance of the chi-square statistic and p-value in the context of the hypothesis testing. So it's all about the context. You need to know what are you doing. Do you find the p-value? What does that p-value stand for? What are you trying to find? What are you trying to compare? These are all really important in AP statistic. Oh, all right, last unit. Unit 9. Finally, we're almost finished, guys. Inference for quantitative data. Slopes. So, condition for linear inference here. Linear. The relation between variables should be linear. Independent observations must be independent from each other. Normal. For any fixed value of explanatory variables, the response variable should follow a normal distribution. Equal variance. The variance of response variables should be the same of all values of the explanatory variables. Randomness. Data should come from a well-designed random sample of a randomized design. See? Random. It's all about being random. Estimating parameters. This is the equation. We have the slope. We'll be using beta, and the intercept will be using alpha. We'll be using the least squares method. So basically, mathematically speaking, for a set of data points with x and y, where x1 is the explanatory variable, y1 is the response variable, sorry, the regression line can be represented as y equals alpha plus beta x, where alpha is the intercept and beta is the slope. Now, inference about the slopes. T-distribution. Hypothesis testing here. So your null hypothesis, which your beta will be equal to 0. So when your beta equals to 0, that means there's no linear relationship. Your alternate hypothesis should be your beta does not equal to 0. If it does not equal to 0, that's a two-tailed test since it's on two sides. It can be on both sides. If b greater than 0 or b less than 0, this indicates a linear relationship, which is a one-sided test. T-statistic. Calculate T-statistic to compare the estimated slope of the null hypothesis. Your p-value, you'll be using the p-value to make decisions about the null hypothesis. Last but not least, the confidence interval. You'll need to construct confidence interval, which now should be a piece of cake for you, for the slope to estimate a range of plausible values for the population slopes. Now, this next important concept is you'll be able to decipher the difference between significance and practical. For significance, it is its focuses on the real-world impact or relevance of the observed effect. On a contextual interpretation, it basically requires understanding the subject matter and considering whether the observed effect is meaningful or useful in practice. Now, in terms of the effect size here is to measure the magnitude of the observed effect or difference. So large effect sizes are more likely to be practically important. Okay? So next we'll be moving on here. So what is practical sorry. So what is practical importance here? Practical importance basically means it shows that an effect exists in a study. So it shows that the effect is large enough to be meaningful in the real world. So the effect needs to be large enough so for it to be in the real world. The effect is large enough to be meaningful in the real world. Okay, that's the key difference. So let's look at the example here. This is let's go through example questions. A researcher conducted a study to investigate the relationship between study hours, which is an explanatory variable, and exam scores. That's the one we're trying to test. That's the result trying to find, which is response variable. For a group of students, after collecting data from a sample of 30 students, the researcher performed a linear regression analysis and obtained the following results. The regression equation, y equals 5.2x plus 70, standard error of a slope, which is which is the beta, which is wait, how do I hold up? Trying to okay, never mind. Hold up. Trying to get back to the. Wait, how do I go back to the Okay. We'll go back to the question later. Because I don't know how do I return to the questions here. I'll do it to return to the previous page. But I'm just gonna go through the key concept and skill first. So for linear regression. Linear regression is a statistical method used to model the relationship between two quantitative variables. It assumes a linear relationship between the explanatory variables, which is the independent variable, and the response variable. It assumes there has a linear relationship. So for inference procedure, it is for linear regression involve hypothesis testing and confidence interval construction for the slope coefficient. These procedures assesses whether there is a significant linear relationship between the variables. Condition for inference. To perform an inference for regression slopes, certain condition must be met, including linear. It must be linear. It must be independent. Normality, equal variance, and the randomness of the data. We'll go through that lots of times already. For interpretation of results here, statistic significance of the slope coefficient does not necessarily imply practical importance. It is essential to interpret that the slope coefficient in the context of the data and the research questions is and the research question to assess its practical relevance. Last but not least, prediction and analysis. Regression analysis allows for prediction of the response variable based on the value of the explanatory variables. Additionally, residual analysis can be used to evaluate the adequacy of the regression model and identify any patterns or outliers in the data. All right. Um. So, thank you. So we're finally finished. Thank you so much for your watching. This is the final review. You can watch this before the AP exam testing. Hope this helps. Hope you all got a 5. I hope this video really helps a lot. Help you summarize this video summarize all the content uh, taught in the AP statistic throughout this year. And I hope you guys will be able to do well on the exam. And of course, like once again, this is a summarized review video. Of course, I'm not gonna cover all the concept taught in AP statistical through all the type of questions, but I did my best to cover the main key concept of each unit. So I hope this helps a lot. And thank you so much for watching. Please subscribe. Thank you. Bye bye. See you next time.